when we left off, I sound like a TV show. Where we left off last week, we were talking about conservation of things in reaction. There's conservation of energy, and there is conservation of mass or conservation of matter when we deal with chemical reactions. Now, in a chemical reaction, we convert matter to a different form of matter by transferring electrons. That's how it's done. But there can't be a detectable change in the total quantity, because you're not changing the atoms themselves. You're just changing who the atoms are connected to. So whatever change in connections you make, you should have the same number of atoms coming out of a reaction that you had going in. Now that's true of a chemical change where electrons are moving around and changing partners, atoms are changing partners, and also true for physical changes. So if someone were to ask, what's the difference in a chemical change and a physical change, what would you say is the difference?
Chemical change is like the physical change is no matter is changing. The chemistry change is no elements are changing.
Well, I would say when water melts, I mean, that's the matter's changing, wouldn't you say?
But,
and it's going from a solid to a liquid.
One is
the matter is. Go ahead.
But the matter is still H2O. But
right.
It just changes from state to state.
Exactly. Yeah. So in a chemical change, the matter actually changes. It is no longer if you have hydrogen and oxygen and you have a little spark, you don't have hydrogen and oxygen after that anymore. They turn into something different. That is a chemical change. And that's something I found that when I was volunteering in high schools, that high school students really had a hard time with, was that when figure when you boiled water and it turned into a gas, that gas was hydrogen and oxygen. It was a remarkably high number of believe that. So yeah, that's one thing we have to remember, is that no matter what the change is, the mass is going to be the same at the beginning and the end. And we're going to use this a lot when we're, in fact, in your second or maybe third lab, we are going to use this principle in order to measure the mass of an unknown quantity of a particular chemical, because we're going to add chemical B and make chemical C, and by measuring the mass of chemical C, we should be able to figure out how much of the unknown we have.
Excuse me.
Yeah.
Have you figured out why the question I left the last class for why 2544 plus 500 is 3044? And why and when we change it to scientific notation, 2.544 times 10 to the third plus 5.
Oh yes, yes. Send it to me, and I'll explain it to you. Okay.
Okay.
Yeah. Send me
the chat. Oh.
Yeah. Where are we? Okay. So this is a couple of examples of why of how that happens. So if I was to take all the things you need to make beer and put it in a beer bottle, sugar, water, malt, hops, yeast, put it all in the bottle, put the cap on it, and then it turns into beer a few days later. The mass of that beer bottle will be exactly the same as it was before, even though before it didn't have any bubbles, it didn't have any alcohol in it, and the sugar had been converted to ethanol. All of those changes take place, but the mass would be precisely the same. And it's true of a car battery. I don't know if you know how a car battery works, but you have, why it's so damn heavy is because there's lead in there. So you have these big pieces of lead and sulfuric acid. That's H2SO4. That's one of the things we're going to be learning about this term, is how to recognize strong acids and bases and some of the chemistry. So H2SO4 is a strong acid, sulfuric acid. So that's why you don't want to be, if you're going to be opening up a car battery, you're going to want some eye protection. So what happens is that the sulfuric acid dissolves some of the lead and forms lead sulfate. And then when you add electrons back into the battery, it turns back into solid lead. And so you go back and forth between lead, Pb, and lead oxide, PbO2, and lead sulfate. And you're just basically moving back and forth, whether you're taking electrons out or putting electrons back in. Then no matter what you're doing, putting electrons back, you're allowing electrons to flow in one direction or flow in the other direction. The mass of your battery is going to be exactly the same, because whether the reaction's going in this direction or going in this direction, the mass either before or after has to be identical. So, if that wasn't the case, eventually, your battery would weigh nothing after just the plastic after a certain period of time. And believe me, your car battery weighs a lot.
I'm a technician, I know.
Yeah, heavy, right?
Yep.
And a pain. Like, yeah, if like one of my cars, I haven't driven in months, and yeah, it's a pain trying to get that thing charged up.
Oh yeah.
So let's break down basically what some of the most simple things we're going to be dealing with. The simplest thing we're going to be dealing with is the elements. Now, when we look at the periodic table, there's going to be all the elements that we know on there, and a lot we don't know. But the basic definition of an element is a pure substance that you cannot break down into anything else by any chemical change. So, for instance, water, if I add electricity to it, I can split it into hydrogen and oxygen. If I have a car bumper that's rusty, I can add substance to that to convert the iron oxide back into iron and shine it up. An element, you can't do that. You can't add any particular reagent, acid, base, chemical, whatever, that can break down, say, pure iron into another pure substance. That can't happen. You could add additional elements to it. You could make iron oxide. You could make a whole bunch of different compounds from it, but you can't turn it into another element. And so these are some basic ones here. Mercury, we pretty much are familiar with mercury because it's the only liquid metal at room temperature. So there's mercury. Arsenic, arsenic. Arsenic is a metalloid, and we'll be talking about the different classes of compounds. We have metals, nonmetals, and metalloids. Lovely smelling sulfur here in the middle. And then bismuth, which if you have a bad stomach and you drink that pink liquid, like I do sometimes, that actually has bismuth in it. Bismuth is an extremely heavy metal. And most heavy metals are extremely toxic. Like, you would not want to drink lead. You would not want to drink uranium. But for some reason, bismuth is good for you. And there's a lot of it in, and the mechanism of how bismuth works to calm your stomach is still kind of unknown, but it works. And then here we have iodine. We don't say iodine. If we say iodine, I have an old chemistry professor that will come back from the dead and slap me. So it's iodine. And iodine is one of those strange elements that doesn't have a liquid phase. So it's at room temperature, it's a solid. And if we were to heat it up, it would go directly to a gas. And we call that sublimation. And we'll get into that a little bit later. So elements in the same family or group, and those are the columns in the periodic table. And believe me, we're going to spend forever staring at the periodic table, because the periodic table basically has all the information we need to do, like, 90% of the problems in this class. There's a lot of information there that you probably aren't aware of right now. But elements that are in the same column, and we call the columns up and down families or groups. They share similar chemical properties, and we're going to learn why that is a little bit later in the third chapter. It's about oh, go ahead.
And why I see the mercury a little bit red?
Probably because some of it's oxidized.
Okay.
On the sort of the layer on the top, you're going to have some mercuric oxide,
Okay.
and that's going to be a different color than
Okay.
than pure mercury. Yeah, you also notice there's some schmutz on the sides of the glass too, which also could be mercuric oxide. You'll find out that one of the things we're going to learn is that oxygen is extremely reactive, and that especially with metals, and that oxygen reacts with pretty much all metals very, very quickly and forms compounds with them. So if you leave anything out in the air, it's going to get oxidized, depending on what element it is, either super, super quickly over a period of time.
Excuse me.
Mm-hmm.
So I heard someone saying that mercury was toxic before, but mercury doesn't dissolve in water or acid. How would that be toxic?
No, it doesn't, but its compounds do. And so if you turn mercury into an ion, so mercury generally has a +1 charge. So that would be actually mercuric oxide there. When mercury is an ion, it then becomes soluble in water. And when it's soluble in water, it's quite toxic. Mercury, the element, is not particularly toxic. It's like you said, it's not particularly well absorbed into the body. But mercury also can react with a lot of organic compounds. It reacts with sulfur. It reacts with a lot of different things.
Okay.
And when it forms it actually can form a gas with particular organic compounds. And then under those conditions, it's pretty
mercury
nasty.
gas can be toxic, right?
Super toxic. Yeah. That's why everyone's probably familiar with the Mad Hatter from the Alice in Wonderland. Everyone's heard of the Mad Hatter from Alice in Wonderland. The reason he was mad because hatters used to use mercury to make felt for hats back in the 19th century, and so these people who made hats would be in the presence of mercury for 12, 14 hours a day, and the vapors would go into their brain and make them insane. And so that's why the Mad Hatter is mad because of mercury.
Professor?
Yeah.
So was there any benefit for taking mercury tablets?
No.
Okay.
No, not that I can think of. I mean, there's been a lot of snake oil over the years. Radium was considered something that people should take for good health back in the 30s and 40s. And we can see that probably wasn't such a great idea.
Yeah.
So yeah, there's a lot of these things. Not so much anymore. I mean, although you see it now, a lot of snake oil salesmen selling like a colloidal silver as a cure for coronavirus and all these other things. Generally you don't need silver in your diet. Silver does have antimicrobial properties, but it doesn't have antiviral properties. And so, yeah, that's a myth. So there's about 118 elements. It's always changing. The reason for that is only about 90 of these occur naturally. You'll just basically, dig them up and find them somewhere. And the rest of them are created in nuclear accelerators, and a lot of them happen here in the Bay Area. There's elements called californium and berkelium. Wonder where berkelium was invented. Lawrencium at the Lawrence Livermore Lab. So there's about 5 or 6 elements. Seaborgium is another one that were invented right here, invented or discovered. It's kind of hard to say. That were made right here in the Bay Area. And how it's done is that you take a target, basically, of heavy metals. It could be lead, it could be whatever. And then basically you bombard it with a beam of particles made up of other atoms. So you fire atoms at other atoms. And what you hope happens is that one atom, the nucleus of one atom, will hit the nucleus of another atom, and we'll see why that is like an incredibly rare thing to happen, because the nuclei are so damn small, and then fuse. So not only do the two nuclei have to hit each other, which is really unlikely, but then once they hit each other, they have to fuse together rather than split apart, which is, again, also unlikely. So it's why you don't see elements being made all the time. Like maybe 1 or 2 every couple of years, a new element will be made. The reason that people keep doing that is that all these elements, basically everything above uranium is unstable. They're radioactive. And so they don't last particularly long. Some of these new metals, some of these don't last very long at all. There's like a couple of microseconds. But it's thought that, according to physicists, and we all know how crazy they are, eventually the nucleus will get to a point where it will achieve stability. And so everybody's trying to see if that's true. They're trying to get up to about, it's supposed to happen somewhere between element 132 and 135, where supposedly an island of stability will emerge, and we'll start to get all new metals that are stable with a whole bunch of new weird properties that we don't know anything about yet. So everyone's very excited about that. So we keep trying to make them. So here's our periodic table, and you're going to see a lot of these different. I would urge you, go to ptable.com. That's a great place to, if you're working on a project or problems, or writing a lab, or whatever you need to do. It's a great place to have everything all together, and it gives you all the information you need, like how many electrons does it have? Where are the electrons in it? What's its density? What charges does it generally make? All that stuff is all right there. So when we're talking about families, basically we're talking about these, a particular group, all going up and down. So what
Excuse me.
Yes, go ahead.
Someone asked in the chat that
Oh, good. Glad you're paying attention to the chat. I can't at the same time. What's going on?
a lot of elements made in that way, they are radioactive.
Mm-hmm.
Why?
Because they're unstable. So any nucleus that isn't stable, and like the vast majority of all these elements are stable until we get up to, where is uranium? Yeah, uranium is down here, right down there. So almost all these elements up to there, with the exception of technetium, which is real. I've always found this interesting. All of these elements they can have radioactive isotopes, but the sort of the basic form of the element is non-radioactive, except technetium, which is weird. I haven't had, this is sort of something beyond the class because it's more of a physics thing, than a chemistry thing because it involves the nucleus. But so this one is radioactive, and then basically everything above uranium is radioactive. All of these are radioactive because the nucleus is not stable. We don't have the right number of neutrons and protons that can hold it together. And that's one of the 4 basic forces. That's not something we're really going to learn too much about in this class, but there's gravity, there's electromagnetism, there's the nuclear strong force, which holds a nucleus together, and then there's the nuclear weak force, which determines radioactivity. And those are the only 4 forces that we've actually discovered so far.
Professor, I had a question.
Go ahead.
Why are the last 2 transition metals on the end, La, Lu, Ac, and Lr, why are they directing towards the inner transition metal? That'd be a really easy question.
Sorry, I didn't. Oh, these 57 to 71
Yes.
and 89 to 103.
Yes.
Yes, these are the super rare earth metals. So we call those we'll find out a little bit later that all of these groups. So we've got, notice that there's a group of 2 right here. And then we go across the periodic table and there's a group of 6 right here. And then in the middle, there's a group of 10. And then on the bottom is a group of 14. We're going to find out exactly why that is. It's everything to do with how
The
electrons are organized. Yeah, in subshells. And so we have the S shell here, which has 2 electrons. We have the P shell here, which has 6. We have the D shell, which has 10. And then down here on the bottom, we have the F shell that has 14. And so that's the reason why we take these, the F block, we call these the different blocks. We take the F block out is because if we didn't, the periodic table would be like 8 feet wide. And so we basically just sort of pull it out and put it on the bottom just so that the thing wouldn't be too insanely wide. But that's why it's sort of taken out there. Yeah.
I think that person's meaning is why man-made elements are radioactive.
Oh, but yeah, because they're extremely unstable.
Okay.
Yeah, I mean that's the thing. I mean, basically, you're asking for a small nucleus to penetrate a larger nucleus, and then fuse with it, and then there's probably a reason why we don't find these things, just because they're so incredibly unstable. Another interesting thing about the periodic table, and I'm taking way too long with this, but I think I find it fascinating, is that elements up to iron here are formed in our sun. So we can find all the elements in the sun, all the way from hydrogen up to iron. And we'll learn how we can do that. That's something I always thought I couldn't understand when I was a kid. How the hell do they know there's
Fusion.
manganese on the sun? Well, we'll learn how you can figure that out. But all the elements up to iron can be found in the sun, and then nothing heavier than that. So pretty much everything heavier than iron up until, let's say, uranium are found in supernova. That's where they come from. And so basically all these elements come from supernova. And that is why when you look at the elements that are present on Earth, you find out that they're pretty abundant till you get up to iron, and then the abundance drops off rather quickly. It's basically the only places they can come from are supernova and basically things hitting our planet from outer space, which I always find kind of trippy. That gold and platinum and all that kind of stuff comes from outer space. So it's all kinds of cool stuff in chemistry you don't think about. So other thing, it's sort of basically we want to take away from this that I sort of skipped over entirely, is when you look at hydrogen, here they sort of give hydrogen in the middle. When we look at it, oops, let me go back. We have So that is the basic information on the periodic table. You get the atomic number. And what's the atomic number?
The number of proton.
Mm-hmm. The number of protons in the nucleus. The number of protons in the nucleus defines what the element is. Not the number of electrons, not the number of neutrons, just the number of protons. And so the atomic number is always going to be a simple number. It's just going to have 1, 2, 3, 4. It's not going to have 0.5 or 0.6 because you can't have half of a proton. That doesn't happen. So then you have the symbol, and so we're sort of familiar with the symbols. They're all going to have 2 letters at the most. One of them has to be capitalized. First letter's capitalized, the second one never is. What's the difference between the atomic number and the atomic mass? What's the atomic mass?
The atomic mass includes the number of electrons alongside the number of protons.
Includes the number of neutrons. The number of electrons, the mass of an electron is so small that it really doesn't add to the mass of the atom at all, really. It's just basically, it's about 4,000 times less than the mass of a proton. And so the mass of an electron really doesn't add anything. It's protons and neutrons. And so, yes, the atomic mass is the number of protons and neutrons. And so, but why is it 1.008?
Because it's an average.
Average of what?
An average of a big sample of this element.
So why are they different? How can they be different?
It's an average of the masses of the isotopes.
Ah, so what's an isotope?
It's the same element, but with a different number of neutrons.
Bingo. Man, you guys are on top of your game today. Yes, different number of neutrons. So hydrogen has 3 isotopes. Hydrogen, which just has no neutrons at all.
And
D, right. What does D stand for? You know what it is?
I just know it in Chinese. I don't know it in English.
Deuterium. So D is deuterium, and it has 1 proton and 1 neutron for a total of 2. Its mass is 2. And then there's tritium, T. It has 1 proton and 2 neutrons. So it is a mass of 3. And this is radioactive. So the question before is like, why are things radioactive? It is the ratio of neutrons to protons. If there's too many, if there's too high a number of neutrons compared to protons, that leads to instability and radioactivity. So a 2-to-1 ratio of neutrons to protons is too many. And so tritium, even though it's a really tiny nucleus, there's only 3 particles in it. It's not
Hydrogen
stable.
has
It breaks
another.
down.
Hydrogen actually has a P.
Just a proton.
Okay.
Yeah, the hydrogen atom is just a proton in the middle and 1 electron. It's the simplest element and the most abundant element in the universe. If you go out into the universe, you'll find hydrogen basically everywhere because it's the easiest element to make. There's only 2 things in there.
Mm-hmm.
All right, let me clear. Okay. So atoms, molecules. This is like not new in information. But the idea of the atom is really, really much, much older than you would think. Goes all the way back to the 5th century BCE. The Greeks came up with the idea of something that you cannot break down any further. Basically, it was the smallest thing in the universe you could possibly come up with that maintains the chemical properties of that thing, whatever it is. So if you had a piece of gold, an atom of gold to them would be the smallest part of that you could break it down to, and it would still be gold. And it turns out that's correct. That's absolutely correct. Even though they had no idea what an atom was, or how it's made, or what electrons or protons were, that was correct. So 2,500 years ago, bingo, you nailed it. But it wasn't until, another 24 centuries had gone by and John Dalton came along and actually showed quantitatively. And of course, if you're going to do any kind of science, it's got to be quantitative. You got to be able to measure something. You got to have a hypothesis. You've got to do experiments, and you've got to validate that hypothesis, and then come up with a mechanism. And Dalton did all of these things. In fact, Dalton, I kind of like to everyone. I had a professor in grad school who would go over all the different scientists we were talking about. I found it fascinating because most of them are completely insane, and it kind of makes sense that people who think that they're smarter than the rest of the world are a little bit crazy. And actually, Dalton was particularly normal. It's mostly the physical chemists who were completely nuts, and the inventor of the periodic table, which I'll get to a little bit later. He's one of my all-time favorite chemists. So Dalton came up with the idea of the atom and defined what an atom is, and we name the measurement of the mass of molecules is actually now called a Dalton. So if you're going to go into biochemistry, and hopefully you all will after you take organic, you'll find that we measure the mass of biological molecules, and basically all molecules, in Daltons. So a Dalton is the mass of one hydrogen atom. We call that a Dalton. And so a big, like proteins and stuff, we measure them in kilodaltons and megadaltons, but it's always in Daltons. So that's an atom. Molecule, just a collection of atoms that are sharing electrons. That's the key to all of chemistry, actually, is how they share electrons. Some share electrons nicely, and we call those covalent bonds, where electrons are shared between two atoms. And then we have ionic bonds, where one atom just steals all the electrons from the other and becomes charged. And that's an ion. Very good. That's actually part of our recitation for this week, is learning the difference between an atom and an ion and how we actually write those down. So an ion, like fluorine, when it's fluorine, it has 7 electrons in its outermost shell. We call those valence electrons. We'll talk more about that a little bit later. But when it becomes an ion, it takes another electron from somebody else. And we'll learn that fluorine is the best of all elements. It's stealing electrons. It's really good at it. It becomes negatively charged. And when it's negatively charged, it's no longer an atom. This is an atom. This is an ion. What's the difference between an atom and an ion?
Charged.
One's charged, but does that mean it has more protons?
No, that means there's more electrons.
Or less. Or less. Right. So fluorine has a property that we call electronegativity, meaning it steals electrons and it makes itself more negative. And then on the other side, you have things like sodium, which don't like all the electrons it has. In fact, it wants to get rid of one. It desperately wants to get rid of one. It wants to get rid of one so bad that if we take sodium metal, and you've probably seen this on YouTube, and if you haven't, you really should. You throw sodium into water, it explodes because it gives away that electron so energetically and becomes positively charged. So the difference is an ion has a different number of protons and electrons. An atom has the same number. And so it is chemically not charged. It's electronically neutral. Sodium has one less electron than protons. And so it is a net number of protons plus 1. Fluoride ion has one more electron than it does protons. So it is a net one more negative charge. And so we put a negative there.
Excuse me.
Yeah.
How do you call H negative in English?
Oh, hydride.
Hydroid. Okay.
Yeah, yeah, we'll get into that a little bit later. Hydrogen doesn't form negative ions very often, although it can. And so any negative ion, we put an IDE at the end.
Okay.
So carbide, sulfide, oxide, fluoride, chloride. Anytime we have an IDE at the end with a charge, it's going to be negative. Okay, but that's like chapter 2.
But how do you
Skipping
call
ahead.
H plus?
We just call that hydrogen ion. If it's positive, we just say the name of the element plus ion. So sodium ion, hydrogen ion, potassium ion, calcium ion. If we just say ion, that means positive charge. If we say IDE at the end, it means negative. But like I said, we'll get into that next chapter a little bit more. So these are, we can actually see atoms now. We have microscopes that allow us to visually see atoms. And so we got a gold nugget here, and a scanning tunneling microscope. Basically, what it will do is we pull out a probe, like a glass probe or a metal probe, so fine that it basically will go down to a surface and make contact with an atom and basically follow the atoms in between. We see it go up and down when the atoms get bigger or smaller. And so with this, on the B side, we can see individual atoms, and we can see them. They're all sort of, packed together with about the same distance in between. And we'll learn about, with metals. We're not going to learn too much about metal chemistry, because that's an inorganic chemistry. If you're interested in that, you'll take classes in inorganic chemistry later. But metals bond in a particularly interesting way with other metals, where they just basically share electrons by the billions rather than just one or two. So they have all these atoms, nuclei, just sort of sitting apart from each other, with electrons basically swimming all around them. That's why metals are such good conductors of electricity, because the electrons are always moving from one end to the other. So only a few elements exist as individual atoms. There's not that many. Usually, and that's because when we learn about electrons like to be organized in particular ways. They like to have a certain number of stable, just like the nuclei are stable or unstable, depending on the number of protons and neutrons. Elements, the electrons, are stable if they achieve certain numbers. And so generally, atoms don't have that number of electrons, and so they go into chemical reactions. If elements can share electrons with another atom of the same element, they will form compounds. They will be elemental molecules, meaning there's no other element in there. And you can see that almost all elements exist as compounds with other atoms of the same element. One of the few that does. Can anyone think of elements that don't do that, that are very stable by themselves?
The eighth was that raw or something?
Yeah, that's the eighth group.
Yeah.
Who's in it?
Argon. No,
Yep,
that's
argon, helium, neon.
Helium.
What do we call them?
noble gases.
Noble gases, right. Yeah, the noble gases, they have the perfect number of electrons. So they
In
don't
China,
wanna...
we call them lazy gases.
We call them noble here because, nobles like to sit on their ass and not do anything too. So yeah, they're also lazy. I like that. I'll have to remember that. Yeah, they have the perfect number of electrons, so they don't want to give any away, and they don't want any more. They have the perfect number. And so they exist perfectly happy as atoms, and they're one of the few elements that actually does that. Here, basically all gases, except for the noble gases, exist as molecules. And we'll see that, like hydrogen is H2, and oxygen is O2, and chlorine is Cl2, and nitrogen is N2. You see a pattern?
Mhm.
Basically, they will share electrons so that each atom has the right number, and so they achieve stability. And we'll learn that the magic number is either 2 or 8. And 8
Oxygen also can
in
be
Chinese
3.
is very lucky too, right? 8 has a very particular.
Yeah, it means to be wealthy.
And it's true in chemistry. Maybe that's why people in China do so well at chemistry, because they realized 8 is wealth, 8 is good. 8 in chemistry is the magic number, and we'll talk about that in the next chapter. Basically, all atoms want to get to either 2 electrons in their outermost shell or 8. And by sharing electrons, they can do that. Yes.
What do you call the oxygen 3?
Ozone.
Ozone.
Ozone. Yeah. Ozone, very, very reactive. You don't want to, there's a reason why ozone is considered a pollutant. And when we draw the different molecules and how the electrons are shared, we'll see why ozone is extremely reactive. You don't want to breathe a lot of it in.
Professor?
Yeah, go ahead.
Is ozone what causes oxidation?
No, oxygen does. But ozone does is involved in like oxidation-like reactions. But it also, ozone's very destructive to organic molecules.
But the atmosphere needs ozone, right?
Yes. Yes. Yeah, the ozone layer actually, one of the things that makes ozone so active is that it has a double bond, which is able to move very, very quickly. And it has what's called a radical. It is a single electron that moves very, very quickly. And it happens to actually also interact with UV radiation.
Okay.
And break down into oxygen. And so it does 2 really good things. It blocks UV radiation and makes more oxygen. So it's like, it's a doubly good thing. So when we're doing reactions, we have to remember that when we have hydrogen reacting with oxygen and making water, it isn't hydrogen H and oxygen O. It's hydrogen H2 and O2, because that is the most stable form of those elements, not H. H is very reactive. O is very reactive. H2 and O2 are much more stable. Okay, so we'll deal with that a little bit more later too. But you have to remember that almost all elements are collections of the same atom in some form to make a molecule. That room, like phosphorus here, P4. Sulfur it's interesting. Sulfur has 8 atoms linked together in its most stable form. You get that stinky yellow form. So atoms and all kinds of molecules move as a unit. So we can't just pull hydrogen off of water. It would no longer be water, and it would take a lot of energy to do that. So just move some of this stuff. Oops, move some of this stuff out of the way. So CO2, glucose, all these things have different combinations of atoms and different elements, and they always have them in definite. Once we start to figure out how we can determine the size of these elements, we'll see that they always are in integers. So we're not going to see something like an element that has,
Half.
you know, C2H5O2.5. You can't have half an atom of oxygen. If you were to figure out that this was the ratio of carbon to hydrogen to oxygen, what would you do in this situation?
Double.
Right, you'd multiply everything by 2 and find out that it's actually C4H10O5. Because you can't have half an atom of something. There's no such thing. And so we'll learn that when you measure the mass of these elements and figure out of these compounds and figure out how many atoms there are of each one, that even if the ratio turns out to have a half or a third or 2/3 or something in it, when we figure out how much it really weighs, we're going to have to take that into consideration. We're going to have to multiply this by 2. If we get like a third of an atom, we'll have to multiply that by 3, or 2/3 of an atom, we'll have to multiply that by 3, or a quarter of an atom, we'll have to multiply that by 4. So we'll get to that when we figure out the masses of these different compounds.
Mhm.
So pure substances and mixtures. We're going to be dealing with mixtures a lot in the class, because pure substances, we don't really find these very often. We find things like, you know, seawater. We're going to find these, you know, mixtures of all sorts of different things all thrown in together. Now, the difference between them is that a pure substance has constant composition. So what does that mean? It means I can take a portion of any of it, and it'll give me the exact same thing. And it only has one type of element. It can't be broken down into anything else. So pure gold, pure phosphorus, pure oxygen. It always has the same composition. It kind of makes sense. And there's only one type of atom there. Now with compounds, there's two. You can break those down into simpler things because they have more than one type of element bonded together with electrons. So the properties of those compounds are different. So if I have something like silver chloride, so it's made from silver and chlorine gas. Silver is a solid, chlorine gas is a gas, obviously. I put those two things together, I come up with a dark compound, whereas silver, very, very shiny, silver chloride isn't. And in fact, it's this reaction that led to the discovery of black and white photography. The old film used to be coated with silver. And so they would be exposed to light.
Oh,
They would have a
speaking
light-sensitive reaction, and then you develop it with chlorine. Yes.
speaking of color,
Mhm.
why iron powder is black, but pure iron is silver? Like,
Iron powder is black.
I think
You mean the iron shaving?
Oh yeah. Probably because the iron shaving is now iron oxide. Once you if you make something like, if you grind something up so that its surface area becomes like really, really, really high, it makes it a lot more reactive. And so oxygen has a chance to react with it much more. If you have a big block of iron, oxygen can only react with a very small layer of it outside. If
surface.
you grind it into super, super small shavings, it oxidizes almost instantly. So I think it's probably iron oxide,
okay.
I would think. All right. Now let's talk about mixtures a little bit. So here's a compound, and we can break it down just by heating it. So here we have mercury oxide, and here's, like, you can see the change in color. We noticed that someone noticed before that there seems to be a reddish tinge. on the mercury. That was a really good observation. Here, all of the mercury has been converted into an oxide. But we can reverse that reaction just by heating it up. And so this is called a decomposition reaction. Why is it called decomposition? Because it's decomposing. It's taking a compound and decomposing it. It's breaking it apart. And so this is what the reaction would be. So I've got mercury 2 oxide, and I heat it. And for that, for heating, we make a little
Delta.
Delta, very good. And that breaks down into solid and O2. So that we also have to balance it. So two moles of metal and a mole of gas. And you can see it happen. So here you see this sort of little silvery drops on the side of the tube. That's liquid mercury.
Mm-hmm.
Solid, look at me. Liquid mercury, and then you can't see it, but then the oxygen gas would be escaping from the top.
Excuse me.
Yeah.
With heat, would that be gas?
Would that be a gas?
Mercury.
No.
Okay.
No, because mercury doesn't become a gas till a much higher. I mean, some of it. I mean, some tiny amount of it. But yeah, mercury doesn't become volatile doesn't completely turn into gas until a much higher temperature.
Okay.
And we'll learn about that in one of phase changes in a later chapter.
Its boiling point is very high.
Yes, all metals have a very, very high boiling point because they share those electrons. That sea of electrons keeps them together. So that's why it takes a lot of energy to melt pure metal.
Mm-hmm.
So the difference between a substance and a mixture is that basically a pure substance has something that can't be separated only by chemical means. So if I have like a pure, like sugar, if I have a sugar bowl and it's filled with sugar, that could be 100% pure sugar. There's different atoms in there, but there's only one kind of molecule. And the only way I could pull that apart is by doing some sort of chemical reaction. Mm-hmm. Now, a mixture, I can separate physically. So, and the example I always like to use is seawater. I can separate water from seawater very easily just by boiling it on my stove. So I just take some seawater, pour it into a pot, put it in the stove, turn on the gas, and I can separate the
oil and water.
Oil and water. I can boil off the water, or I can, if it's a short enough oil, I can boil off the oil, depending on which one.
Or you can just pour the oil out of the.
Yeah, or if they separate, you can just physically remove them. So that would be a physical thing. You could either they separate and you could just scoop them out, or you could boil one and leave the other one behind. Those are all physical changes, okay? And so those would be mixtures, not a substance. That's a mixture. And there's two types. There's homogeneous and heterogeneous. Now, what do you figure the difference is between those two?
Homo means same, hetero means different. So,
right. So what would be a homogeneous mixture?
Homogeneous mixture means all the parts are have the same components, same percentage of the components, and like a solution would be a homogeneous.
Right. It's basically what it means is that just like with the pure substance before, I can take a sample from any part of a homogeneous mixture and it will be identical. So as long as there's nothing falling out of solution, if I have a solution of salt water, it's just NaCl and water. If it's all dissolved, I could take some from the top of the glass, I could take some from the bottom of the glass, and it will be identical. There'll be the same number of water molecules and the same number of sodium chloride ions in the sample. A heterogeneous mixture isn't like that. It would be like if I took a sample from the top, it would look different from the sample at the bottom because it's not uniform. It has to be a homogeneous mixture, has to be uniform all the way up and down. A heterogeneous mixture isn't uniform. Like if I had like a pile of mud, it would be different from different parts. It would have a different amount of dirt in it. It would have a different amount of water in it. It wouldn't look the same all the way through.
Rust.
It would depend. I mean, rust is just iron. It's just a compound.
I mean, a rust can be multi-compounds.
It could be, yes, it could be different. It could be iron 2 oxide. It could be iron 3 oxide as well. But if you had a mixture with a little bit of what we call precipitate in it, that would be a heterogeneous mixture. If something was falling out of solution as a solid, that means we could like swirl it up. It would be mixed up top and bottom, but if we let it go for a while, the solids would then sink to the bottom.
Yeah.
Then we could have, then it would be different from the top and the bottom.
Mm-hmm.
So yeah, salt water, homogeneous mixture. Doesn't matter where I take it. It's gonna have the same amount of salt in it once it all goes into solution. But a heterogeneous mixture would be like this jar of jelly beans. It's going to have more yellow ones at the top and more green ones at the bottom. It's not the same. It's not uniform all the way through. Like basically, the air we're breathing right now is not a homogeneous solution. You may be surprised to find out that air is a solution too. It's a solution of gases, but it's still a solution. And usually on a good day, it's homogeneous, right? Because it's, you know, it's got the same amount of nitrogen and oxygen and argon and CO2 and everything else in there. But today, there's also a lot of solid particles in it, and it's not uniform. So like one breath you take is probably going to be different than the next breath you take, depending on how the wind is shifting. It's no longer a heterogeneous mixture, which is kind of nasty.
Someone is asking, what about a supersaturated solution?
A supersaturated solution is also uniform until you introduce one more crystal. So for instance, you could have a supersaturated sugar solution, right? So basically what that means is that you make the solution at a high temperature where you can dissolve a lot more stuff because things are more soluble usually. Solids are more soluble in hot solvents than cool solvents. So let's just take the saltwater example here. So at room temperature, let's say I can dissolve 10 grams of sodium chloride for every glass of water. If I was to boil that water, make it really, really hot, I could probably dissolve maybe 2, maybe 3 times more. Then when I let it cool down to room temperature, nothing, and don't disturb it, I would have more sodium chloride than a normal room temperature solution of sodium chloride would have. It would now be super saturated. It's still homogeneous because you can't tell from the top to the bottom where more sodium is. However, the minute I try to take a sample and put a spoon in, that would cause the crystallization to take place. Or if I dropped one more crystal of salt in there, it would immediately start falling all out of solution. Then it would be heterogeneous because I would have solid salt
in the
crystals
bottom.
on the bottom, no longer heterogeneous. That's a really good question. And super saturated. People have been thinking about this. This is excellent. So yeah, I'm going to leave it there. We didn't really get super far today, but we had a lot of interesting discussions, and I prefer that anyway. So
I like it too.
any questions about this or where we're going next? you will see, if you look at the Canvas page, and I hope you have, I'm going to skip a lot between, like chapter 1 is going to follow the book, chapter 2 is going to follow the book, and then I completely leave 3, 4, and 5 because we're going to cover that as we go. Basically, it's just about how to measure different concentrations of things and how to, I mean, we're going to be doing that as we go anyway. How to balance chemical reactions. We're going to be doing that anyway.
Someone is having a question, James, in the
Yes,
chat.
go right ahead.
How are actual tests going to work again?
How the test's
Yes.
going to work?
Mm-hmm.
Yeah, that's a good question because last term I gave people like way too long to do the problems, and basically found that everybody was just, everyone was just looking up the answers online, which, you know, what can you do? I can't really criticize you from doing that. I'd probably do the same thing myself.
Everyone gets 100%.
Well, no, but everyone gets the same answers, and answers that using terms that we never discussed in class. And so that was a little disturbing. So I'm going to talk with AJ Bates about it. I think what we're going to do is probably just have a shortened period, just have like the test would go out. I would release it on Canvas. You'd have like 2 or 3 hours to do it and then send it back.
One of
I think that's how we're going to do it.
professors did that way. Like everyone turns their camera on, and people are just copying, and not copying, just doing the problems in the paper. And
Yeah, I'm not a huge
It's so
fan. I'm not a
same
huge fan
thing,
of that,
kinda.
but I mean, yeah, I don't think that. Yeah, I need to figure out a different way. I think just giving like 2 or 3 hours to do it is good, because generally in class we'd only have 90 minutes, right? So, but that makes it a little tricky, because what if someone's, you know, computer explodes, or, I mean, because this is always happening, right? Your Wi-Fi goes down or something comes up. So I don't want to, you know, and if that happens in the middle of a test and then you run out of time, that's not fair. So I figured maybe give 2 or 3 hours. I haven't decided yet, but it'll probably be something like that.
okay,
Yeah.
just
Professor-
an idea.
Sorry? I didn't quite
Professor,
hear
I
that
had a
last
question.
comment.
So my area has been getting notifications of possible blackouts.
Uh-huh.
Can I do the quiz through my phone Canvas, or it has to be on the computer?
You can do the test. Generally, what you do for the test is, stuck these way too far in here. You get the normal test. Some people just print it out and then just write the answers on it. If you don't have a printer, you just get a piece of paper and just write out your answers on it. So what you do is, if your computer's down or whatever, and you just have a calculator, which is what you'd have in the class anyway, just take a couple pieces of loose leaf or whatever, that you write the answers down. Don't bother writing out the questions again. Show all your work, take a picture of it, and there's smartphone apps that will turn pictures into PDFs, and then just submit it. Yeah, so you don't even need the computer. You can just do it with your phone.
Okay. All right.
Yeah.
Thank you.
Yeah, that works just fine. Yeah, has there been any blackouts? We got back about 5 days ago, and there hasn't been any yet. Are there? Where are you that there's like you've got a blackout notice?
I'm in San Bruno, just right by down the hill from Skyline. I haven't got any yet, but I keep getting emails and text messages saying that your area could possibly.
Oh man, I need to check my phone. Yeah, I'm in Pacifica. I'm not terribly far from San Bruno. That's
San
right down
Mateo-
the hill.
San Mateo also got a bunch of blackouts for like an hour or two.
Oh,
Yeah, I
man.
agree with San Mateo blackouts,
Oh
actually.
man, so our lab could be fun this afternoon.
Yeah, hopefully there's nothing happened today, so we're good.
Yeah, we're already on fire. Do we need this too? I mean, come on. This just isn't right. Anyway, so I will see my group at 1:10. The other group, hopefully, AJ has gotten in touch with you. I think you're having discussion about labs first, and then he's going to take you through how you'll be able to pick up the kits. You won't be able to do it today, obviously, it looks like, because I think the campus is shut down because of the air quality, but you should be able to get them by the end of the week.
We had to sign up for like appointment times, so that they're on Wednesday for tomorrow and Thursday throughout the day.
Yeah, well, yeah, it's assuming that the campus doesn't burn down. Just too many things happening at once. I can't keep track. All right.
Okay. Thank you, James. Have a wonderful day.
I will see you soon. You also have a wonderful day, and we'll talk to you soon. All right. Stay well, everyone. And,
Thank you, Professor.
Stay not burning.
Thank you, Professor.
All right. Bye-bye.